Welcome and hello. This is a video exercise in HEC-RAS, and in this exercise, we are going to be using a 2D flow area to model a river reach. All right, so we're going to start from the very beginning this time. We're going to start with our HEC-RAS interface, go up to File, New Project, and then navigate to where you want to save your project files. Okay, and then in the title, go ahead and type in the title for your project. I'm going to call this exercise 32 and then click OK and then click OK. All right, first what I want to do here is I have the geometric data editor open, but I want to go to HEC RAS Mapper. So go up to GIS Tools and then RAS Mapper. All right, so here's my RAS Mapper window. That opened up just fine. Let's go ahead and start by creating a geometry. So I'm going to right click, create new geometry. I'm going to call it base, click OK. And then here's the manage layer associations box opens up, but I'm not ready for that, so I can access that a little bit later. Let's start by adding a projection. So project set projection. Now what I'm going to do is add a projection I already have saved and downloaded and I've been using for multiple exercises and lessons already on my computer, which I have saved in this file right here. It's going to be a .prj file, and you can go ahead and go to this spatialreference.org webpage right here. It opened up on my other screen, but yeah, go ahead, download the PRJ file for wherever on planet Earth that you are modeling your HEC-RAS project, and then go ahead and navigate to it, load it up, and then you'd be good. So click apply, and then click OK. Next, what I want to do is download some USGS terrain data for my area of interest. And where I decided to model this particular program was over here. I've got a push pin right here on the bridge. This is Google Earth, but there's lots of different mapping programs where you can just get the latitude and longitude values of your location. So what I'm looking at here is 39 degrees north and 121 degrees west. I'm going to put my cursor exactly over this bridge here. I'm not too interested in the bridge at the moment, but I do want to use this river reach to just model the river. So I'm going to go ahead and put my cursor over this river. And then at that same time, I'm going to take a look at this north and west value, convert it from degree minute second to degree decimal, and then carry on from there. So the latitude is 10.23 seconds. So we'll divide that by 60 plus 8 minutes, divide that by 60. And that will be 39.136 degrees north. And then I got a negative 121.582 degrees west. So that's Western Hemisphere. That's longitude. All right. So we got my location down. Next, we're going to go ahead and right click on terrain, download terrain data, USGS. And the reason for all that latitude longitude business is because the source extent is going to be based on latitude longitude. If you have a shapefile, a geometry, or the current view, you can use those options as well. I'm going to go with lat long and then click on this button over here to specify the upper left coordinate, and then the lower right coordinate is going to be coming up right after this. 39.163 and then negative 121.582. I'm going to actually use the same values for the lower right corner as well. 39.163. Okay. And then click OK, and then click on Query Products. It looks like there are two different tiles here with the 1 meter data. I'm going to use this 1 meter cell size. This is going to save in my terrain directory in a directory called USGS. So let's go ahead and click download and get that started. Okay, so it tells me here download complete. I'll click OK, close this dialog box. Now I want to load those USGS files into my RAS Mapper. So to do that, I'm going to go ahead and right click, create new RAS terrain, and then navigate to those files. So here is my project directory, and click on terrain, click on USGS. Here are the two TIFF files that I just downloaded. So I'll click OK, and then I'm going to go meters to feet. Everything else looks good, and then click create and wait some more. All right, that import was complete now. I can go ahead and click close, and now I see my terrain right here. Now what I want to do is zoom in on my area. Looks like it's right down here. So this is my bridge location. Here is the river that I'm interested in. Now let's go ahead and sketch out a 2D flow area on this map. Now to do that, I want to use my geometry that I've created. Click on the edit pencil, And then right here, I have 2D flow area. So go ahead and expand that. Let's start with a perimeter. So click on perimeter, make sure I'm in edit mode here. And then let's go ahead and start maybe right about here. Maybe this crossing right here, probably another bridge. The 2D flow area is going to extend well past the main channel. It's going to also include some overbank area. So I'm going to probably move that up here, then down here. This looks like a levee, so I'll just kind of cross over to the backside of the levee. Now let's move the map over, just pan. Then this is probably a good downstream boundary right here. Cross the river, and then just go past this levee, sort of on the backside of the levee. That way it'll include all the overland flow. And then just stop it right here with a double click. All right. The name, I'm going to call this 2D flow area, and then click OK. Now it's asking me for the computation point cell spacing, dx and dy. Now it's starting off at 100, and I'm using US customary units here, so that would be 100 feet. That's probably too small for this large of an area, so let's go with something larger, maybe like, let's see what 500 feet looks like. So I'll click on Generate Computation Points, then click Close, and now zoom out a little bit. And yeah, I think that's pretty good. Maybe 300 or 400. Let's go ahead and click on Edit, right click, Edit 2D Area Properties. Now instead of 500, let's see what 300 looks like. It'll definitely be more cells, smaller spacing, and click Yes to say that you do want to override the previous 500 cell spacing. All right, so that's smaller cells. That looks good. In this dialog box, we do have a Manning's N of 0.06, which is default, but we're going to download a land cover layer and then assign different Manning N value based on land type. So don't worry about this right now. We'll get to that. All right, so let's go ahead and click close. I'm happy with this 2D flow area mesh of 300 feet. But what I want to do is for the main channel, add a refinement region is what it's called. And then sketch out just the main channel and give it a much smaller cell size so that there's more detail. Let's start with the upstream reach, just to zoom in here. Sketch right here and here, maybe just up along the banks. And I have to zoom out and pan over. So this doesn't have to be precise. Again, this is just an exercise, and I can always edit it later if I don't like it. Okay, so here's the downstream end. Go ahead and click here, cross the river, and then continue up the other side and double click to finish. I'm going to call this main channel because if I was sketching out a river section line with bank lines, what I effectively just sketched out here was the bank lines. All right, so for that refinement region, I'm going to go ahead and click on the edit, and then for the right click on the refinement region, edit refinement region properties. Now for cell size, dx and dy, I wanted to make it smaller than 300, of course, because that's the cell spacing for the entire 2D flow area, but not too small. So let's go ahead and just take out 50 feet and see what that looks like. So I'll go ahead and click OK. And then I also need to enforce. So right click, enforce all regions. And now what you see here in the main channel is we have a number of smaller cells based on that refinement region and the cell spacing that I specified. So that looks good. You can see the transition from the 50 feet up to 300 feet. So it'd be 100 and then, or 200, I guess, after that. This would be the 200 size. This is the 300 size. That looks good. I'm happy with that. Next, what we want to do is put in some boundary conditions. So on the upstream boundary condition, I'll go ahead and click on boundary condition lines. And then I want to click edit. Looks like I'm already editing. That's good. And then click on add. And then just sketch my boundary condition line. I'm only going to use the main channel here. So double click. I'm going to call this upstream and then click OK. And then I'll add another one to the downstream end. All right, so here is the downstream end, adding my boundary condition line, single left click to start, and then a double left click to terminate. I'm going to call this downstream and then click OK. All right, so stop editing, save the edits. Next, what I want to do is add a land cover layer. So if you go to, there's a web page I have saved here, land cover. This is mrlc.gov/data. I'll leave this link in the description of the video. And what I've done is just gone down to continental United States, or I guess I could have selected Western United States, and then wait for it to load. And then what I'm going to download here is the land cover data for 2023, or if you're doing this at a later date, then you may have the 2024 data or some later years. Doesn't matter, that's fine. Click on download, let that download. I've already downloaded it, so I'm not going to have to wait, but once it is downloaded, you're going to come over here to map layers and then right click, add new RAS layer. Land cover layer is what I'm adding. Now for the extents, I want to use the geometry or current view. Actually, let's go with terrain. Not terrain, that's too much. Let's go with geometry. That's fine. The terrain would be fine too, but geometry is a smaller area and we don't care anything outside of our geometry as far as the land cover goes. I'm going to click on this plus button here and then navigate to where I have my land cover data. And it's this TIFF file right here. Mine was 1.4 gigabytes, so it's a pretty good size. But once I bring it into my RAS project, it's not going to be much smaller because it's cropped out by the extents of the geometry. Okay, that looks fine. The cell size doesn't need to be quite that small. That's 10 feet. I'll just go ahead and make it 50 feet, which is the same as the cell spacing within the main channel, and then click create. Okay, so that was nice and quick. Close that. I'm going to come back to this layer association dialog box in just a moment. Here is the land cover data. So let me toggle off the terrain so we can see the land cover in isolation here. All right, so this is what it gave me for the land cover. It's just an outer bounding rectangle for the containing the 2D flow area that I sketched in. And then here's the 2D flow area right here. Next, what I want to do is define the Manning's N value and percent impervious for each land cover type. So to do that, I'll click on land cover, right click, edit land cover data table. And as you see here, I have a column for ID, land cover type, Manning's N, and percent impervious. So just to make it easy for myself, I like to sort ascending because I have this data already saved in ascending order. If you don't have numbers here, you can look them up, or I've also provided a link to this page in the HEC-RAS 2D Users Manual. And if you scroll down about halfway into the page, right here, there's a table of values with what looks like the exact same IDs and names. And then here's a column for the Manning's N and the percent impervious. So yeah, I'll go ahead and leave the link to this page in the video description as well. All right, so let me go ahead and grab my data. Okay, I've copied it onto my clipboard, and then if I just highlight Control V to paste, that's good right there. Okay, so I'll go ahead and click OK. Now I have my layer for Manning's N value, and I want to return to that layer association dialog box that was popping up earlier. So I'm going to go up to Project and then Manage Layer Associations. Here is my base geometry, and by default, the one and only terrain layer that I have is associated with that geometry, just by default, that's fine. For Manning's N, I'm going to select land cover because that's the land cover. That's the layer that has Manning's N data. And then percent impervious, I'm going to also select that same land cover. Next, we want to do infiltration. So we can create an infiltration layer based on the land cover. So I'll go ahead and do that now. Map layers, right click, add new RAS layer. And now this is going to be infiltration from land cover or soil layer. There's also an infiltration shapefile option if you actually have a file. But what we're going to do is generate that infiltration based on the land cover. So I'm going to select deficit and constant for my infiltration method. There's a few other options though if you want. And then for land cover, I'm going to select that land cover. All right. It's going to create this file inside land classification directory called infiltration.hdf. So just give that a moment. Okay, looks like it's already done. That was cool. So if I wanted to see the infiltration map, here's that right here. If I click on it, I should get numbers. These are just ID values. But what I need to do is now specify that infiltration data for each land cover. We know the land cover type. We know the Manning's N and percent impervious, but we don't know the infiltration properties yet. So to do that, I'll go ahead and right click, edit infiltration data table. This is a similar data table that we saw before with the same first two fields of ID and name for land cover. But now we need to specify the minimum deficit, initial deficit, and the percolation rate. I'm going to go ahead and just paste in the values that I had saved on my clipboard. Not a whole lot of variability, but whatever the actual numbers are, this is where you put them in. Now I want to associate this infiltration layer with my terrain, with my geometry file. So I'll go up to Project, Manage Layer Association once again, and then for infiltration, I can click on my infiltration layer. Well, we're going to return to RAS Mapper after running results, or if there's other input that I need to do here, which I just forgot about. But for now, I'm just going to go ahead and hit save. What I need to do is specify the boundary conditions for both upstream and downstream. Let me get my terrain layer back on here. There we go. There's the terrain layer, just looks a little bit better. To do that, I'm going to go up to edit and then unsteady flow data. Now this is a bug, I believe, in RAS 6.6. Or maybe it's not a bug and I'm just doing something wrong, but I don't have any upstream or downstream boundary conditions showing up in my dialog box right here. Where did they go? I'm not sure, but I have realized that I can make them appear if I open up the geometric data editor and then go File, Open Geometry, select my geometry here, base, click OK. I don't really care too much about this right now, but now I should be able to go up to Edit, Unsteady Flow Data, and then boom, here is my downstream and upstream boundary conditions. All right, so let's go ahead and start with downstream. This is going to be a normal depth type of downstream boundary condition where it's expecting me to type in my slope. This is the energy grade line slope. For now, let's just go ahead and go with 1% on that energy grade line slope. I'm going to type in 0.01 and click OK. All right, so for the upstream boundary condition, I'm going to use a stage hydrograph and then type in the numbers right here. Let's see, to know what numbers to use, let's go ahead and go back to our RAS mapper. Here's that. And then for a feature, I'm going to go ahead and just click on profile line and then edit. And just sketch a profile line here. Profile 1 is fine. I can call it upstream profile. I'm going to go ahead and select that profile and then just take a look at the data. Okay, so this is a little bit unfortunate because it's just reading the water surface itself. So we're going to be running this model on top of the existing water surface. But in a real world situation, you'd have better geometric data. You'd have the bathymetric data to add to the LiDAR data. All right, so let's go ahead and just say the stage starts at 45 and it goes up to 60 and then back down to 45. So that would basically just sort of be like a hydrograph of sorts, but we're using the stage. We could be more dramatic and increase the height to something like 80, but let's just go ahead and keep things mild here for the first 2D exercise. All right, so back to that boundary condition. I'm going to click on stage hydrograph, stage hydrograph. I'm going to start it at, what did I say, 45? And then let's go a few hours, 45, and then let's ramp up to 60, and then back down to 45 here. And then now I'm going to just go all the way down to 3 days, which is 72 hours or 73 hours to get an extra point, and then type in 45. All right, so click on interpolate missing values, and then it auto fills in those values, including the values between the 2 points, like 45 up to 60. Oh, look at that, just exactly 15. That comes down exactly 1 per hour, 1 foot per hour. All right, so if I wanted to look at the data, I could click on plot data. This is the stage and as a function of time. This is the 3-day time horizon of that simulation. All right, so that looks good. For the start time of this stage hydrograph, I'm going to use simulation time by just using the default selection here. That's fine. All right, click OK. All right, so I'm going to go ahead and File, Save Unsteady Flow Data. For the title, I'm going to call this Stage 45-60-45, just to kind of help me remember that what the stage data is in this file by looking at the file name. All right, so go ahead and close that. Something else I want to do is specify the warm-up period. So when you're running models with a 2D flow area or a 1D and a 2D flow area, it's good to include a warm-up time. I'm going to go up to Run and then Unsteady Flow Analysis. And then in Options, actually first I should probably save this plan and then I'll make that change. So File, Save the plan. I'm going to also call this Stage 45-60-45. Then copy, OK, paste, OK. So it's also the short ID. Now for that warm-up period, options, computation options and tolerances. And I'm going to click on the 2D flow options, and then down here on line 11 is the initial conditions time. This is the warm-up time. Let's go ahead and say 4 hours. I think that should be sufficient. And then click OK. I'm going to toggle on my geometry preprocessor, unsteady flow, and post processor, and then start this. It's going to be a 3-day time window. Doesn't really matter when. I'm just going to use the first 3 days of the year 2020. So the end time would be the 4th at the beginning of the day. And then for all these other settings, I'm just going to go ahead and use them as they are, the default values. So go ahead and click Save, and then click Compute. All right, so it's doing the geometry preprocessor. All right, let's see here. Boundary condition line downstream intersects the perimeter of the 2D flow area. This is not allowed in HEC-RAS and so on and so forth. Okay, I messed something up, guys. Let me go ahead and fix that. That sounds like a HEC-RAS mapper problem. So let me go down to my downstream edge right here. Oh yeah, it does. Okay, it does. That was my mistake. Didn't realize that. I need to be a little bit more careful when I sketched out this downstream boundary line. If you didn't have this problem and you're still working, then just wait for me for a moment. I'm going to click on boundary condition lines right here. Click on edit, and then click on this edit right here. And then let's see if I can just double click. Okay, so I'm going to move this point outside. That's good. It shouldn't really affect anything else though. Let's see what happens here. So I'm going to save the edits by clicking stop edits, say yes right here. And then, yeah, so the geometry should have saved. That's good. I think everything else is good. Let's go ahead and run it and see if we get that same error message. So run, unsteady flow analysis, nothing else to change here. I'll go ahead and click compute. All right, that was successful. No error messages, no warning messages. We're looking good. Go ahead and click close and then close that. Now let's go ahead and take a look at some results here. So let me zoom out in my RAS Mapper. We'll look at the results in RAS Mapper. I'm going to actually turn off some of these geometry elements like the perimeter and the refinement region and we can keep boundary conditions. That's fine. Don't need the 2D flow area either. We have a results menu. I'm going to expand, click on results, and then expand my plan, which is called stage 45, 60, 45. Click that on, and let's go ahead and click on depth. So here's the maximum depth, this blue coloration right here. What I'm going to do is expand this a little bit further here, and now I can go ahead and run the simulation. So the water increases and then decreases because the hydrograph, of course, went from 45 feet up to 60 feet, at least at that upstream boundary. And what I like to look at is just to see how the water covers up this island and some of the other areas down here. I'm going to go ahead and change the speed, slow it down a little bit. Close that, and then let's go ahead and run that simulation once again. So are we running? Yeah, it's just a little bit slower. It's a 1 hour time step, so it could have been recorded the results at a smaller time window. So to do that, I would go up to run, unsteady flow, and then instead of 1 hour right here, I could have made this maybe 10 minutes or 6 minutes. Let's go ahead and go with 10 minutes and then compute it. Okay, that finished up again without any errors as expected. Let's go ahead and run the simulation now. So this is using the 10-minute time step. So we're going to have 6 times as many frames. So we'll speed this up a little bit, close, and then click the play button. Okay, yeah, you can see that the animation is much more smooth and gradual by recording results 6 times as many as the previous run. All right, so this is still the end of the second day right here. It's still running. It's just a constant flow. This is the beginning of the third day, sort of the middle of the third day now. All right, I'm going to go ahead and stop that. We can also look at individual results. So with the depth layer selected, I could go right click anywhere on the map, plot the time series, look at the depth. That makes sense. We have a constant depth with the constant flow. There's not a lot of lagging or attenuation because this is such a short reach as well. I could also sketch out another profile line. So if I had like a river station or something, I could go ahead and name it that. But here is my profile line 2. I'll click OK. Now, if I wanted to look at the results for that profile line, let me go ahead and zoom in, click on it, right click, plot time series, something like flow. Okay, so that's sort of uneventful, but it does give you the flow rate as function of time. If I wanted to view some other parameters, I'd just have to check them on in the table of contents down here. So we have depth, velocity, water surface elevation. Now, if I go right click on my profile line 2, I can select something like velocity. That'd be pretty good. All right, so this is cool. This shows the velocity profile along that profile line. So of course there's no velocity where there's no flow, which is the first 160 feet. And then we actually have the water, which has a maximum flow or speed of over 6 feet per second. And then of course it goes back down as the water becomes shallower and then the water ends. So this stationing right here from 0 up to 700, that should be visible if I go to profile lines. Okay, I need to move this up a little bit. Profile line 2, and then I click on the plot tick marks. I can actually zoom in and then see that 160 was right about here. And then it looks like it stops 680, maybe 700. So we definitely have some slower velocities. as the water approaches the bank here. Okay, I could do the same thing for any other location. Like this location would probably be pretty interesting with what looks like a sandbar here and some shallow flow, and then probably deeper, faster flow over here. All right, well, that was it for this exercise. What we did was build a 2D flow area model in HEC-RAS to simulate the flow of water through this section of the river.